Now that you've learned all the derivation rules of sentential logic, we're going to look at a few problems that involve more complex solutions, namely having a subderivation inside a subderivation. The rules for nested subderivations are exactly the same as subderivations on the main scope line. You can bring things in leftward from previous or rightward from previous lines by reiteration or referencing other rules, as long as that other line isn't inside a subderivation that is already closed, where the premise has been discharged. When you end a subderivation, you take something out of it using the subderivation rule and move back one scope line. The rest of the lines inside that subderivation that you've just closed is off limits once you end it. It's important to remember that you can move scope lines one at a time, and that the conclusion you're trying to get for the whole derivation must be back on the main scope line. This will all make more sense as we work through some examples. If you want, you can pause the video after each problem is introduced to try it on your own before we go through it together. So here's our first problem. We need to derive A if and only if C from these three premises. Since the sentence we're trying to get is a biconditional, the strategy I would recommend is biconditional introduction. The first step in biconditional introduction is to assume A and prove C. Now we need to use the three premises and A to somehow prove C. Now we clearly can't get C using any of our straightforward rules. So we're going to do the strategy I always recommend if you don't see another way. Assume the opposite and then find a contradiction. Since we're trying to get C without any modifiers, we're going to assume the negation of C for negation elimination. We need to get a contradiction inside of this subderivation so we can get C back out on the scope line under A. So what contradictions do we have? We can get A on line 6 by reiteration from line 4. This is permissible because we're still inside that subderivation for biconditional introduction. Now we need the contradiction. We can get it's not the case that A by conjunction elimination from line 3. And now we have the contradiction between A and not A. So we can move back one scope line and get C on line 8 by negation elimination. Now I want to just acknowledge here that we didn't actually have to use it is not the case that C at all. We already had a contradiction with our premises by introducing A because we have it's not the case that A in that conjunction on line 3. It may feel weird or like cheating a bit to use a contradiction we already have just to prove whatever we want, but it's absolutely a legitimate move in logic. Remember all the way back to the first lessons in this course. Any argument with inconsistent premises is valid because it's truth preserving. You can never move from true premises to a false conclusion if it's impossible for all the premises to be true. Logicians call this the principle of explosion. Once you have a contradiction, you can use it to prove anything. The important thing to note here is that we can only use it to get things inside of that subderivation under A. If we move back to the main scope line, the premise A will be discharged and that subderivation will be closed, so we won't have a contradiction anymore. So we've used contradiction to prove C from A. Now we need to stop that subderivation and go back to the main scope line. If we were trying to do a regular conditional introduction, we could get if A then C on line 9. But we're trying to prove A if and only if C. So we need to do a second independent subderivation. This time, we assume C and try to prove A. And remember, we can't use anything from lines 4 through 7, since that subderivation is closed. Hopefully you can see where we go from here. We have C as our assumption on line 9, and we also have it is not the case that C as our premise on line 1. So we have a contradiction that we can use. So on line 10, we assume the negation of A for negation elimination. Now, just like we did before, we get the contradiction inside this subderivation by reiterating C from line 9 and it is not the case that C from line 1. Now that we have the contradiction inside of our subderivation for negation elimination, we can go back one scope line and use that rule on line 13 to get A by negation elimination from lines 10 through 12. So now we've got two subderivations that are both right up against our main scope line, one that assumes A and proves C, and one that assumes C and proves A. Now on line 14 on our main scope line, we can use biconditional introduction to get A if and only if C from lines 4 through 8 and lines 9 through 13. Now let's look at another problem. We need to derive A if and only if B or C from the premise A if and only if B and A if and only if C. Since our conclusion is a biconditional, just like the first problem, we're going to do two subderivations from biconditional introduction. For the first one, we're going to assume A and then prove B or C. Since we're trying to prove the disjunction B or C, we know if we can get one of those disjuncts on their own, then we can use disjunction introduction to get the other. I'm going to try to get B, but you could have done it with C instead. Since I have A and I'm trying to get B, on line 3, I'm going to use conjunction elimination to get A if and only if B from line 1. Now we can use biconditional elimination to get B on line 4 from lines 2 and 3. Now I do want to note we had to do that step to use conjunction elimination on line 3. You can't skip it and use biconditional elimination straight from line 1 because the sentence on line 1 has a conjunction as the main connective. We had to get A if and only if B on its own, which has the biconditional as the main connective, to be able to use biconditional elimination. This is true for all of the derivation rules you've learned so far. You can't use them on only parts of sentences. It needs to be the main connective of the whole sentence on the line you're referencing. The last step in this subderivation is to get B or C. We can do that using disjunction introduction to add or C to B from line 4. So that half of the proof for the biconditional introduction was pretty straightforward. Now we need to go back to the main scope line and do the other half. We need a new separate subderivation assuming B or C, and now we need to get A on this scope line. So how can we get A from the disjunction B or C? I'm going to do it by using disjunction elimination. Remember, this rule also requires two subderivations, one with each disjunct as the assumption. On line 7, we're going to start another subderivation by assuming B. Remember, we can't use anything from the closed subderivation on lines 2 through 5, but we can still use the main premise on line 1. So on line 9, we can get A if and only if B by conjunction elimination from line 1. And then we can get A on line 9 by biconditional elimination from lines 7 and 8. Now we go back one scope line and repeat the process with an independent subderivation assuming the other disjunct, C. We can get A if and only if C by conjunction elimination from 1. And then on line 12, we use biconditional elimination from lines 10 and 11 to get A. So now we have the disjunction B or C on line 6, and we've proved A follows from B with our subderivations on lines 7 through 9, and we've proved A independently follows from C with our subderivation on line 10 through 12. So on line 13, still inside the scope line from our assumption B or C, we can get A by disjunction elimination. Now let's look at what we have so far. Directly against the main scope line, we have the subderivation that assumes A and proves B or C, lines 2 through 5. And then we have the subderivation that assumes B or C and proves A, lines 6 through 13. So on line 14, we can use biconditional introduction to get A if and only if B or C on the main scope line. Hopefully talking through these problems has given you a good feel for how to work problems involving nested subderivations. If you're still unsure of how they work, please check out pages 167 through 187 of the logic book. I'm also going to plug the strategies for derivations and in sentential logic document that you can find under course resources on the modules page. It's a great guide for learning how to approach different types of arguments and different types of goal sentences when doing derivations. For recommended problems, I have two sets. The first two problems give you all of the lines of a derivation and just ask you to fill in the justifications on each line. The second set of problems ask you to construct your own derivations. I'll go over all three of these problems in the review video. If you have any difficulties or questions, please bring them to class, come to office hours, or otherwise reach out. We're here to help you.